Reinforcement learning requires a clearly defined numerical reward. If you want an AI to play chess, a win is a 1 and a loss is a 0. But if you want a robot to clean a room, be useful, or do a backflip, there is no programmable reward function. When engineers try to bridge this gap by writing proxy rewards, like giving points for forward velocity to make a robot walk, the agent inevitably hacks the proxy. It might learn to fall forward and flail its legs to rack up points without ever taking a step. The agent perfectly optimizes the mathematical reward provided, but completely fails the human's actual intent. The technical term for this failure is proxy misalignment, a manifestation of Goodhart's law. One alternative is imitation learning, or inverse RL, where the agent learns by watching an expert. But requiring expert demonstrations is often impossible. A human cannot physically demonstrate how a four-legged robot should walk. In 2017, a team from OpenAI and DeepMind published a paper titled Deep Reinforcement Learning from Human Preferences. Their solution was to remove handcrafted mathematical rewards entirely and instead learn a scalar reward function directly from human feedback. The pipeline requires 3 steps: gathering human feedback, translating that feedback into a mathematical reward model, and then optimizing that learned model using standard deep reinforcement learning. The 2017 paper frames the capture of human intent as a problem of system architecture. By automating the extraction of preferences, the researchers moved the bottleneck from the engineer's ability to write reward code to the system's ability to learn from feedback. If we cannot write a reward function, we have to extract the reward signal from a human observer. The immediate question is what format that data should take. The most obvious approach is to ask a human to watch the agent's behavior and assign it an absolute numerical score out of 10. But absolute scoring fails in practice. Humans are inherently noisy and inconsistent. An annotator's internal scale for a 7 out of 10 will drift over the course of an hour and will rarely match another annotator's scale. Instead of assigning a value to a single behavior, the human labeler is presented with 2 options. The interface presents a human labeler with 2 short video clips of the agent acting in the environment. We can call them Clip 1 and Clip 2. The human is only required to make a single binary choice. Which clip is better? Humans can evaluate comparisons with extreme reliability. Even when judging highly complex or ambiguous behaviors, it is much easier to tell if one attempt is slightly better than another than it is to assign either a definitive numerical value. Discarding absolute scoring for pairwise comparisons forms the foundation of all modern RLHF systems. It successfully translates subjective human intent into clean binary classification data. The agent cannot optimize a binary preference directly. That classification data must be translated into a differentiable scalar reward. To do this, the system trains a reward model, denoted as R hat. This diagram shows how it works. A neural network is mapped over the agent's observation and action space. For each video clip, the model evaluates every step and sums the individual outputs to calculate an accumulated total reward for that entire trajectory. We end up with 2 values, R1 and R2. The paper models the human's preference using the Bradley-Terry rule. The probability that the human prefers Clip 1 over Clip 2 is defined as the sigmoid function of R1 minus R2. This formula is exactly the ELO rating system used in competitive chess. The algorithm is literally rating trajectory clips like chess players. The difference in their ratings provides a direct estimate of the probability that one clip will win the human's preference over the other. To train this reward model, the system uses standard cross-entropy loss applied to the human comparison labels. The loss function includes a flat 10% uniform noise term. This assumes that humans will make an arrow 10% of the time, regardless of how obvious the gap between the 2 clips might be. Additionally, because the Bradley-Terry rule relies only on the difference between ratings, it is invariant to shifts in translation and scale. To keep the math stable, the learned reward must be normalized to a 0 mean and a fixed standard deviation across an ensemble of models. By treating trajectories as competitors in an ELO ranking, RLHF derives a differentiable loss landscape from human preference. Deep reinforcement learning agents require millions of environmental interactions to learn. Generating human labels for every single step would be prohibitively slow and expensive. To scale the process, the researchers designed a system of 3 concurrent asynchronous loops. The first loop is the policy, A standard RL agent continuously explores the environment and maximizes the current version of the learned reward. The second loop manages query selection. It constantly extracts pairs of trajectory clips from the agent's ongoing exploration. It filters these pairs using a variance-based selection rule. The system only sends a pair to the human if an ensemble of reward models heavily disagrees on which clip is better. It seeks out the highest variance, prioritizing the data it is most uncertain about. The third loop is the update. The human labels these highly informative pairs. The reward model updates based on the new ELO ratings, and that updated model is immediately pushed back to guide the active policy loop. Because the reward model is a continuous neural network mapped over states and actions, it generalizes. A single human label effectively informs the reward mapping for thousands of similar, unlabeled states. Between this generalization and the variance-based querying, human feedback accounts for less than 1% of the agent's total interactions. In the complex physics environments of Mujiko, it took roughly 700 human comparisons, about 1 hour of a person's time, for the agent to solve tasks nearly as well as an agent with access to a perfect, programmed true reward. The asynchronous architecture provides a blueprint for running preference-based learning alongside the massive computational demands of deep reinforcement learning. Section 3.3 of the paper outlines a critical vulnerability. It asks, what happens if you break the asynchronous loops, train the reward model offline all at once, and hand that static model to the agent to optimize? The core conflict is that the trained reward model is stationary, but the reinforcement learning policy is not. As the policy learns, it constantly changes the state distribution it visits. An offline reward model only accurately captures the reward landscape visible in the old, previously explored states. When the agent shifts its behavior, it navigates into unknown states. The static reward model, now completely out of distribution, begins hallucinating high values. The agent immediately exploits these spikes, maximizing that fraction of the map and behaving bizarrely. The paper documents a classic example of this failure state when an agent was trained on an offline reward model for Atari Pong. The agent figured out how to indefinitely rally the ball back and forth with the opponent without ever scoring a point. It found a blind spot in the static reward model and gamed it. This failure dictates a strict architectural mandate. Human feedback must be constantly interleaved online with the RL training. The reward map has to update as the policy shifts. A static, machine-learned proxy of human intent is just as dangerous and vulnerable to reward hacking as a hand-coded algorithmic one. When the feedback loops are kept online, the capabilities are vast. The system successfully elicited highly complex, novel behaviors, like teaching a simulated robot to do a backflip, using only 900 human queries. But the paper also clearly documented its limits in more complex environments. On classic Atari games like Space Invaders and Breakout, the RLHF system never quite matched the performance of an agent trained on the game's actual programmatic score. And when relying on real, noisy human labelers, the system completely failed to learn Qbert. Replacing a clean, deterministic mathematical reward with human estimates inherently injects higher variance and instability into the training pipeline. Despite the instability and the limitations on Atari, the 2017 paper established a formula that became the bedrock of modern AI alignment. To scale this framework to large language models, researchers simply swapped video clips of robots for text responses and added a specific statistical constraint called a KL penalty to further suppress the reward hacking trap. The result was InstructGPT. The overarching architecture remains exactly the same today. Extract human intent using pairwise comparisons instead of absolute scores, model that data as an ELO rating using the Bradley-Terry rule, and use asynchronous optimization to ensure the feedback loops stay closed, adapting as the machine learns.